Hey, good morning, everybody. So we're going to start with our first talk of the day. Professor Máté Matolcsi from Hungary is going to talk to us about the properties of the unit distance graph of the plane. So let's welcome him.
Thank you very much. And first of all, I would like to thank the organizers for inviting me and mostly for putting together this conference for the second time. It must be a very, very hard work to organize such an event with hundreds of participants contributing from all parts of mathematics and theoretical physics and computer science. So it's a privilege to be here. And all right, so my talk will focus on unit distance graph of the plane. And so I'll give you a brief overview of how the talk will be constructed. So first I give you the basic notion of unit distance graphs and related parameters and properties and some problem formulations. And then we go on a journey of a hierarchy of linear programs. The first linear program will be that of the fractional chromatic number of a graph. The second will be the so-called geometric fractional chromatic number, something that we introduced recently. And then I'll show you a result of a computer search, a concrete graph, a finite graph on 27 vertices, which achieves geometric fractional chromatic number equal to 4. I will explain why 4 is important in this context. And then we move on to the third hierarchy of the linear programs, namely using some Fourier analysis, and finally proving an old conjecture of Paul Erdos with another witness graph. And I should mention here that all this is joint work with several co-authors, Gergely Ambrus, Adrián Csiszárik, Imre Ruzsa, Daniel Varga, and Pál Zsámboki. And I should also say that the talk does not follow the historical order of the results. So this talk is being put together in hindsight, that now we understand better how the different notions are put together. And so I will be able to present it to you in a way that is hopefully more digestible. So to start with, what are unit distance graphs? It's very simple. First of all, everything in this talk happens in 2 dimensions. In the Euclidean plane, we don't move into 3 or 4 or higher dimensions. We stay in 2 dimensions. It is possible to consider all these notions in higher dimensions, but I'm not going to do it in this talk. So what is a unit distance graph? Well, it's just a finite subset of the plane in which 2 points, 2 vertices are being connected if and only if they are unit distance away. So these are 2 very simple examples. One is a equilateral triangle with side length equal to 1. Then each vertex is connected to each other vertex. And this is the so-called Moser spindle that will come up several times in the talk. So how is this constructed? Well, you take an equilateral triangle here, and then you reflect this to this midpoint, so you get this rhombus. And then you rotate that, so it's this kind of a diamond-shaped rhombus, and you rotate your diamond around this vertex in such a way that the 2 furthermost vertices get exactly distance 1 away. So you move, your angle of rotation is such that this length is going to be exactly 1. In this way, you get 7 points, and you can check that all these edges are really edges, meaning that they have length 1. And no other segments have length 1. So why is this interesting? Well, we will see in a moment that we can introduce several parameters of unit distance graphs that are mathematicians are interested in. The first and maybe the most famous of the parameters is the chromatic number. So by the way, in my notation in this talk, the notation will be sort of simplified. There are standard notations in combinatorics for the chromatic number, usually denoted with the Greek letter chi. independence number, usually denoted by alpha, but I'm not going to use them because it's kind of hard to remember for a talk like this, so I'm just going to basically use abbreviations. Cn is chromatic number, IR is independence ratio, and so on. So maybe it's easier for the audience to follow what notion is being talked about. So what is a chromatic number? Well, simply the minimum number of colors needed if adjacent vertices must have different color. So let's take the Moser spindle. You want to color the vertices in such a way that whenever you have an edge, then the endpoints must have different colors. And you can convince yourself that this Moser spindle is a very simple small graph which needs at least 4 colors. Why so? Well, for the triangle itself, you need 3 different colors, that's clear. And then you can, maybe you can use the, if you want to use the same, if you don't want to use 4 colors, then what is this point going to be? Well, it has to be red, right? Because green and blue are occupied, so this has to be red. Okay, but then this is also green and blue in one way or the other. So this has to be red as well, but this cannot be because then you have an edge with two red dots. So this has to have a different color. I denote it by black. So all together you need at least 4 colors. So that's the chromatic number of the Moser spindle is 4. What about the independence ratio, IR? Well, that's the relative size of the largest independent set in G. So what is an independent set? Independent set is a few points in your graph so that there are no edges whatsoever in between them. So for example, in the Moser spindle, what is this? These 2 red dots, they are an independent set. There is no edge in between them. But if I choose a third one, wherever that third be, let's say I choose this one as a third one, this is not an independent set anymore because there is an edge in here. And you can convince yourself that whichever 3 dots you choose, there will be an edge. So the maximal independent set in the Moser spindle is 2. And when I say the relative size, I mean that I divide by the number of vertices of the graph, in this case 7. So the relative size of the independent set in this case is 2 over 7. That's the independence ratio of the Moser spindle. And there is an easy argument. You can convince yourself in 5 minutes that for any graph, the chromatic number is larger than or equal to 1 over the independence ratio. Well, why is that? Because one color class can only color 2/7 of your spindle. So each color class occupies only 2/7. So if you have 3 color classes, that's still only 3 times 2, that's 6 over 7. You're still not coloring the full set. So you need a 4th color. So this is basically the argument that proves in general that the chromatic number is larger than 1 over the independence ratio. And the most famous problem in this circle of ideas is the so-called Hadwiger-Nelson problem. So that's basically asking what's the chromatic number of the whole plane. So far I was talking about finite graphs, but you can of course do the same notion. At least the chromatic number makes sense for infinite graphs. The independence ratio is not so obvious how to generalize, but the chromatic number definitely. So now you want to color the full plane in such a way that any 2 points which are distance 1 away get different colors. So this hexagonal coloring is actually a good one. You can convince yourself that, I mean, and you have a bit of a freedom of what is the length of an edge of the hexagon. You have a bit of a freedom to choose it. And if you choose it correctly, then this will be a good coloring of the plane. And it uses 7 colors. So we can say that at most 7 colors are enough. And just in the previous slide, we saw that the Moser spindle proves you that you need at least 4 colors. So the answer must be between 4 and 7. What is the correct answer? Nobody knows, but there was a breakthrough recently, about 5 years ago, 6 years ago now, by Aubrey de Grey. He constructed a finite graph on 1581 vertices, which needs 5 colors. So that proves that at least 5 colors is needed. 7 is enough, so the answer has to be between 5 and 7. Still, we don't know what it is. People usually expect that 7 is the correct number. And what did I want to say about this? Well, since then, the number of vertices have come down to a few hundred. I'm not sure what exactly is the smallest number, but still, you need a computer proof to prove that it is indeed 5 chromatic. So let's go to a generalization of the independence ratio. I told you that for a finite graph, independence ratio is the relative size of the largest independent set. So what if we move out to the infinite graph of the full plane? And I'm asking you, what is the largest independent set in the full plane? Well, for the notion of largeness, you need some kind of measure. So for this reason, we invoke some analysis, and we say that we take a measurable subset of the plane which avoids the unit distance, which is called one avoiding. It means that any 2 points of A are not unit distance away. This exactly means that it's an independent set of the graph. And you want to measure how large this independent set is. Well, that's basically the density of your set in the plane. Well, but you might object, if you know some analysis, you might object that, okay, you have an infinite measurable set, it might not have a density. So what is the question really? So if you want to make it precise, you have to define the upper density of a set, and you take the supremum of possible upper densities of one avoiding measurable sets. So that's the precise definition, but you don't actually need to go into too much trouble, really, because with a very easy argument, you can prove that you can assume that your set A is periodic. If it is periodic with a lattice, then it does have a density, and you don't have to worry about upper densities anymore, and you can use more analysis, namely Fourier analysis later. So what is this easy argument that you can make it periodic? Well, with a bit of with a little loss in the density. Well, it's a very simple argument. You give me a set which has high upper density. Upper density means that it has a huge square in which it has a large density. So I cut out that huge square, and I'm going to paste it periodically to cover the full plane. This has the same upper density. But then you might object, there can be trouble when two of the squares touch, there can be points with unit distance. So I ruin my set. But then I say, okay, what I'm going to do is simply delete those strips. On the edges of the squares, I delete. I lose a bit of density by deleting, but only epsilon. You can take epsilon. I mean, the set you can take arbitrarily large. That will make your loss arbitrarily small. So basically, you can construct a set which is periodic and almost the same density. Okay, so from now on, we might as well assume that the set is periodic, which makes life easier. And let's have a concrete example, which is actually the best known example. And I'm pretty sure everyone can cook up this example in half an hour or 1 hour or 1 day, depending on how good your geometric intuition is. But what happens is you sit down and you want to say, okay, let me construct a set which is very dense as possible, and it avoids the unit distance. So what do you do first? I think the first idea is to take a disk of radius 1/2, open disk. So then there is no unit distance in the disk. Every distance is smaller than 1. And then you shift it in a hexagonal lattice manner. You shift it in a hexagonal lattice manner in such a way that the disks are separated with a distance 1. And then any distance within the disks are smaller than 1, and when you connect two disks, the distances are larger than 1, so definitely your set is avoiding the unit distance. And you can calculate the density, and it turns out to be something like 22%, and that's fairly good. But then there is a little trick. This may not be very trivial, but if you think long enough, I'm sure many of you would find this trick as well. That namely, you can just chop your disk a little bit with a hexagon. You lose a bit of an area of the disk, so seemingly you are losing density. But because you chopped off, it enables you to pull them a little bit closer together. And then you are winning because your packing of this is slightly denser. So you are losing a bit by chopping, and you are winning a bit by pulling them together. And you can analyze it numerically. Actually, it's not easy to, well, I mean, to a certain extent analytically, but then to find where the derivative is 0 when you really hit the optimum is not actually a closed expression. It's just a numerical calculation. And then it turns out that if you do it optimally, then you can reach the density of basically 23%, a little bit less, 22.93%. And that's the best construction so far. And people have tried to improve it. Even I tried, my co-authors tried over the years, over the decades. This goes back to the 60s, so like 60 years old construction. And it hasn't been improved, and there is a good, I myself believe that this is actually the best construction. But this much we cannot prove. But there was a conjecture of Paul Erdos about this. Not exactly that this is the best construction, but he conjectured that, well, whatever construction you come up with, the density is going to be strictly less than 1/4. So we saw here that the best construction is basically 23%. Erdos conjectured that, well, I'm not sure 23 is the correct answer, but definitely less than 25. And why did he put 1/4 here? Well, unfortunately, we cannot ask him anymore. But maybe a very simple reason could be that if you go below 1/4 with the density, then obviously you need at least 5 colors for the full plane, right? Because if one color class occupies less than 1/4, then 4 color class occupies less than 4/4. So that means there is some leftover. You need a 5th color. So at least if you are using measurable color classes, you need at least 5 colors. So that might have been his motivation with the 1/4. There is another guess that I can tell you that maybe 1/4 comes to his mind, Erdős's mind, because you can ask the same question if you measure the distance not with a Euclidean distance, but with an L1 distance or L infinity distance. And if you do L infinity distance, then your unit ball is simply a square. And if you ask the same question about L infinity distance, then you can put half squares in a lattice manner with exactly 1/4 density. And then you have a feeling that, okay, this is very nice. It fits just perfectly well because my ball is actually a square. And the density is 1/4, you can convince yourself that that is indeed the highest density in that case. So then the highest density equals 1/4. And then you have the feeling that, well, the Euclidean distance has to be a bit less efficient, right? Because it just doesn't, things don't fit together so nicely. So probably the density will be less than 1/4. So this might have been on his mind, either of these arguments. Anyhow, he conjectured that it is less than 1/4, and it took about half a century to prove this, and we finally achieved this, as we will see later in the talk. So let's go on to a hierarchy of linear programs, because we are gonna give upper bounds on the density of a one-avoiding set by certain linear programs. So how do you do that? Well, so we want to prove that all one-avoiding sets have low densities, low meaning less than 1/4. So what happens? My opponent, say you bring me a set and claim that it has very high density, say 0.26. And I have to prove that you are wrong. How do I prove you are wrong. I'm going to bring a finite unit distance graph X. This will be my witness graph, proving that you are wrong. So what I'm going to do is I randomly drop my graph on the plane, rotated, translated copies. Randomly really needs to define mathematically precisely, but let's jump over it and let's just assume everyone knows what it means. You randomly put, you drop on the plane, and then you take its intersection with the one avoiding set A. And then we record the relative frequencies, and we write up linear constraints on these frequencies. So all these words are better explained by pictures. So someone comes to me with the cross construction and tells me that, okay, this has a very high density, 0.26, whatever. Of course, I know it's not because it's 0.23, but okay, I have to convince myself somehow and convince him. So what do? I come up with a finite unit distance graph. Actually, the finite graph at the end will be much more complicated than this, but for the sake of the argument and the construction, let's just see what happens. So I come up with a small unit distance graph, say the Moser spindle, and I just drop it on the plane. And in this case, the way I dropped it, these 2 points intersect the given set. So I mark on my sheet that, okay, I dropped once and this is what happened. Then I drop it again. Okay, my second drop looks like this. In this case, this was the intersection. Then I drop it again, and I do it a billion times. And I always record what the intersection is. And then it will give me a histogram of the patterns, how many times each pattern occurred. So I take this histogram. So this pattern happened 6.9% of the time. This pattern happened 10% of the time, and so on and so forth. And I make these relative frequencies, and this will be a probability distribution on the independent sets of my small graph. Let's just have 1 minute here. There are 2 interesting things here. Both of them are fairly trivial. One is that I put 0% here. Why? Because this is not an independent set. This is an edge. It never happens, however I drop it, it never happens that those 2 points are in the intersection, because they cannot be in the intersection because those 2 points are unit distance away. So they are excluded from your set A. So this is 0%. So anything which is not independent, which contains an edge, has to be 0%. Whenever something is independent, is obviously a non-negative. And we have a curious fact here that I put 8% and 8% here, both of them exactly equal. Is that surprising? Well, not so surprising, because you see, this is a segment of length square root of 3, and this is also a segment of length square root of 3. And so dropping on the plane to hit my set with this has equal chance of hitting with that. You can convince yourself that if your notion of randomness is good enough, then it has to be true. And then we have a sum of probabilities. There are 2 sums. First of all, if you sum up all the probabilities, then it has to sum up to 1, right? Because something happens. So altogether, you have probability 1. But there is another curious thing, is that if you sum up the patterns which contain a fixed vertex, then of course you will get the density of the original set. Why so? Because, I mean, what are the patterns that can come up which contain this guy? Well, it may happen that only this one is in the set, only this vertex, or maybe these 2, or maybe those 2, or maybe those 2. There are no other options. So when you add up those relative frequencies, then you have to get exactly the probability that that single point is in your set. Because, you know, you don't really care what happens with all the others. As long as this one is in, it will fall into either this, or that class. So when you add up, and you know for sure that the left-hand side is delta, is the density of your set. Why? Because this is simply putting a random point on the plane. it will have a chance of delta, the delta meaning the density of the set. So that's on the left-hand side. And on the right-hand side, well, I'm not sure about these numbers, but they have to add up to exactly delta, right? So and all this gives rise to a linear program. Let's see what the linear program is. So as I said, delta denotes the density of your set A. AI will be your variables. Those are the relative frequencies of independent set I. And what are the constraints? Well, all frequencies are non-negative, obviously. They sum up to 1, obviously, because it's a probability distribution. And we just saw in the previous slide that if you fix any vertex, then those independent sets which contain that vertex, they have a frequency which adds up, to delta. So these are the constraints, nothing else. And we get an upper bound on the density delta by solving this LP, meaning we maximize delta, we maximize this delta under these constraints. So this is an LP which does not depend on the unit distance avoiding set. It depends only on the small graph that I have in my hand. And if you divide through everything by delta, so let's say A prime is AI divided by delta, so I divide everything by delta, then this becomes 1, and this becomes 1 over delta, in which case you want to minimize the summation of all the atoms. You want to minimize 1 over delta in order to maximize delta. And this is exactly the fractional chromatic number. So I hope I put it on the, yeah. So I put it on the next slide exactly what it is. So you are given a finite witness graph X, and you write up the linear program for the fractional chromatic number. So once again, what is it? You want to minimize the total sum of your atoms, subject to each of them being non-negative, and for each vertex, the atoms containing that vertex has to sum up to 1. So that's exactly what the combinatorial literature calls the fractional chromatic number of your graph X. And this is of independent interest in graph theory. Yeah, and the point is that this fractional chromatic number gives a universal upper bound on the set delta, on the density delta A. So I'm bringing my graph X. In this example, it was just the Moser spindle, but actually we will come up with a much more complicated finite graph example. I'm writing up a linear program on that finite graph. It's a finite linear program, and the solution of that will give an upper bound on any of the density of any one avoiding set. So people have tried this. As I said, fractional chromatic number was already investigated regardless of densities, and there have been results. So we just saw in the very first slide that the Moser spindle has, well, we saw that it has an independence ratio of 2/7. You can convince yourself that the chromatic number is 4, and the fractional chromatic number, you can easily convince yourself that it's 7/2, which is exactly 3.5. So that's easy. If you want to pass 3.5, it's not easy at all. And then you just go like this. So it's 3.55 by Fisher and Ullman in 97, and then 3.66, 3.89. Actually, this result, 3.89, was constructed exactly with an upper density, with an upper bound on the density of one avoiding sets. And this gave one of the best bounds on the density. And then there are two unpublished graphs. Both of them are on hundreds or even thousands of vertices, which have a fractional chromatic number reaching 3.99. So it's getting very close to 4, but it's not reaching 4 and definitely not going past 4. So maybe the reason is that the supremum of the finite, the fractional chromatic number of finite graphs is exactly 4, we don't know, but we will have some results on it right in this talk. So let's look at the histogram again. I think I just included these slides again to convince you once again that there is no coincidence that these two numbers are equal to each other, because both of them are the same as the probability of dropping a random segment of length square root of 3 on the plane and hitting the one avoiding set. And this gives the idea of the so-called geometric fractional chromatic number that we introduced a couple of years ago. Namely, we can put further linear constraints on the variables due to the underlying geometric properties of the graph. Namely, whenever you have two congruent copies of the same thing, maybe they are segments of the same length, or maybe they are triangles which are congruent to each other, or quadruples which are congruent to each other, whatever. You have a configuration in your graph which appears at least twice. It appears as k and it appears as j. And then you can, just as before with the 2 square root of 3 having the same histogram probabilities, you can convince yourself that if they are congruent to each other, then the sum of atoms of those atoms where the independent set contains k is the same as the sum of those atoms which contain j. So that gives you, because of the underlying geometry of the problem, it gives you all of a sudden new linear constraints between your variables. So you can define a new concept of geometric fractional chromatic number by simply adding these constraints to your LP. And to prove that the density of a one avoiding set is strictly less than 1/4, all you need to do is to find a graph with geometric fractional chromatic number strictly larger than 4. Because if you remember, there was a division by delta in these linear programs. So the larger you go with these numbers, you take the reciprocal, and that will be the bound on delta. So if you pass 4, then delta will pass 1/4 downward. So your estimate will be better than 1/4. So first of all, let's see some theorems connecting fractional chromatic number, geometric fractional chromatic number, and independence ratio. And the interesting fact is that in the limit, these things behave very nicely. First of all, there are some fairly trivial monotonicity relations for both the fractional chromatic number and the geometric fractional chromatic number. If you increase your graph, you add more and more vertices, then these parameters can only grow. The fractional chromatic number, geometric fractional chromatic, it can only grow. Either it stays the same or it grows. So there is a monotonically increasing order here. And we also have, for every finite graph, as we saw in one of the first slides, that 1 over independence ratio is less than the fractional chromatic number, and it's less than the geometric fractional chromatic number. So these two are fairly trivial. But in the limit, it's not so trivial that these things actually become equal in the limit. So first of all, I should define what I mean. So when I say fractional chromatic number of the full plane, I simply mean the supremum of finite sets, fractional chromatic number of finite sets. And similarly, geometric fractional chromatic number of the plane is the supremum of geometric fractional of finite sets. And the independence ratio of the plane is the infimum of the possible independence ratios of finite graphs. And if you go to the limit, then it's a very clever proof saying that these three things will be actually equal. And maybe I can tell you what the idea of this proof is, because it's pretty nice and it has a curiosity. So I would like to prove that in the limit, the fractional chromatic number is equal to the geometric fractional chromatic number of the plane. So assume that someone gives me a graph X, a small graph X, with geometric fractional chromatic number fairly large, let's say gamma. You can think of gamma, let's say, equal to 4, because that's what's going to happen in the next slides anyway. So someone comes to me and says, look, this is a finite graph with geometric fractional chromatic number equal to 4. Can you construct something which has fractional chromatic number without these geometric constraints, just the fractional chromatic number equal to 4 or at least close to 4? And I say I can. It's pretty easy. What I'm going to do is, here is my small graph, which has geometric fractional equal to 4. And then I'm going to take lots of rotated copies and lots of translated copies of it, billions of it. And I will have this huge graph, let's call it Y. So I'm pasting lots of translated and rotated copies of X. It will be a huge graph of billions and billions of vertices. And the point is that this Y is going to be almost invariant under translations and under rotations. Not quite invariant, because if you translate a little bit, then of course at the end things will fall off in a way, but it will be almost invariant. And because it's almost invariant, you can prove that its fractional chromatic number without imposing the geometric constraints. The geometric constraints will be imposed almost automatically, because it's almost translation invariant and almost rotation invariant. So this huge graph will have a fractional chromatic number which is almost as large as gamma. So if gamma was 4, then my billion vertex graph will have a value 4 minus epsilon. It might not be exactly 4, but very close to 4, as close as you want. And the curiosity that I mentioned is that this proof only works in 2 dimensions, because the 2-dimensional group, the group of 2-dimensional Euclidean isometries has this nice amenability property, which in higher dimension doesn't happen anymore. Namely, when I said at the argument, I said it will be almost translation invariant, and I argued that, okay, something might fall off at the edge, but not much. This is true, but if you go to higher dimensions, then you cannot guarantee this. Too many things will fall off at the edge, so I'm not sure if this proof goes through in higher dimensions. So this is actually an interesting fact that I'm not aware of what happens if the dimension here is increased from 2 to 3, whether it's still true or not. My guess would be that it should still be true, but the proof doesn't work. So I'm not sure. And so here we come to a point of concrete constructions, because we saw that all you need is a finite graph with a large geometric fractional chromatic number. So what we want to find is, well, a finite graph with large fractional chromatic or geometric fractional chromatic number. And we saw just in the previous slide that there is no theoretical advantage of GFCN or FCN, because in the limit they are equal anyway. But there is a huge practical advantage, namely that you might find some small graph with a large geometric fractional chromatic number, whereas you would need to go to thousands of vertices or even millions of vertices to have a large fractional chromatic number. And that's exactly what happens in practice. We launched a computer search, and we found I'm just checking the time. Okay. So we found a graph on 27 vertices which hits exactly 4. Not approximately, but exactly 4 as the geometric fractional chromatic number. And there is another curiosity here. How do you prove that something is exactly 4? Well, it's a value of a linear program. So you have this linear program of thousands of variables, actually hundreds of thousands, something like 150,000 variables and 15,000 constraints. What's the optimal value? So you ask your computer, it shows you numerically it's 3.9999999. So you know that it's 4, but how do you actually prove it? I mean, your LP has only rational coefficients, so in principle there is a rational solution that testifies that it's 4. But how do you actually prove it? You have to find that solution. And the funny thing is that you find a very nice solution of the primal LP. Very good. It gives you 4. You are relaxed. And then you have to go to the dual LP and also find the solution of the dual LP that gives exactly 4. And that's where things get really messed up, and we cannot find a nice, simple solution of the dual LP. What we do find at the end, with a lot of effort and thinking and numerical simulation and everything, at the end we do find rational solutions. So there is no doubt that this value is exactly 4, because now everything is rational, and even though you have hundreds of thousands of variables, there will be no error whatsoever, rational calculations. But it's very ugly, meaning that the rational numbers that appear in the solution of the LP has something like 200 digits in the numerator and 201 in the denominator and things like this. And you say, well, it's not exactly very revealing, is it? But it does testify that the result is 4. But it would be nice to have a more revealing witness. Actually, the solution of the primal LP is very revealing, because it corresponds to a 4 coloring of the underlying graph. So something that you can really understand why the variables take those values, and that's very nice. But when you go to the dual, we don't get anything nice. Anyhow, let's have a corollary of this. Because we found this with exactly equal to 4, we all agreed before that this gives a testification, a witness, that the upper density of any one avoiding set is less than 1 over 4, which is exactly this. This is the same as Erdős's conjecture, almost, except that Erdős's conjecture is strictly less than 1/4. And there is a crucial difference, because if you prove that it's strictly less than 1/4, then you need 5 colors, that's for sure. But if you just prove it's less than or equal to 1/4, then maybe you need only 4 colors. Of course, now we know that you need 5 colors anyway, but that's why it's not. You shouldn't stop here. You should somehow go and go below. So what's the result of the search? This is the graph on 27 vertices. It's not very revealing. It's a unit distance graph, and this has geometric fractional chromatic number exactly 4. Actually, if you calculate the fractional chromatic number without the geometrical constraint, it will just give you 3.5, no more than the Moser spindle. But with the geometric constraints, you actually hit 4. And then you might ask me, how is this number 3 here? It's a vertex with degree 1. Or this number 8 is also a vertex with degree 1. They don't seem right. I mean, you would expect that in these graphs, all vertices have fairly high degrees. Certainly, something with degree 1 is not expected. Especially not expected because how do we get this graph? Well, we start from the Moser spindle, 7 vertices, and then iteratively we build up larger and larger graphs. And what's the step of the iteration? Wherever we stand, I'm going to add a new point, and the new point is only added if it has at least degree 2, meaning that it has distance 1 from at least 2 of existing points. So then you might object, then this is clearly wrong, because this guy cannot be in the picture, because I'm only taking points with at least degree 2, so it cannot be in the picture. But actually, the search is a little bit more clever, because after each step of the iteration, we get a new graph, possibly higher geometric fractional chromatic number, but then we try to throw away some of the vertices. We don't want to increase the number of vertices without reason, so to say. So if I added a point and I observe that there is an increase of the geometric fractional chromatic number, I'm very happy. It increased my target value. But maybe some older points become redundant. So I'm going to kick those out. And that's how degree 1 points are possible, because it may have had a neighbor which was kicked out at one of the points of the iteration. And then we move on to the last bit. How do you go below 1/4? That's the highest hierarchy of the linear programming method. Namely, you invoke some Fourier analysis. So I remind you again that if you if you take a vertex, if you take a segment of length square root of 3, then you can define, so you can define a function fx, so-called autocorrelation function, which is defined as simply dropping a segment of length x on the plane and taking the probability of the segment, both endpoints being in your one avoiding set. So for every x, this defines a number, fx. So you end up with a function, which is a continuous function. If your set was measurable, it's a continuous function. And this is called the autocorrelation function of your set A. And it has a very nice property by Fourier analysis, which I'm not going to explain in detail. But the point is that the autocorrelation function is positive definite, which means that when you expand it in Fourier terms, then the coefficients will be non-negative. So your function fx can be written as a possibly infinite sum of some non-negative Fourier coefficients, kappa t, times Bessel functions evaluated at t times f. And the crucial fact is that these kappas are non-negative. And then this leads to new linear constraints connecting the kappa variables and the atomic variables that we had before. So what are the new? I will show you the new constraints, but let's first observe some trivial equalities. The density of your set is exactly f0. Because what is f0? You put a segment of length 0, that's a simple point, and you drop it on the plane randomly. It has a chance of delta hitting your set. So delta is exactly f0, and it can be evaluated as sum of kappa t's. These omega functions are normalized in such a way that at 0, they take the value 1. So that's sum of kappa t. So in the linear program, we are going to maximize delta, so we want to maximize sum of kappa t. And also, we have f1 equal to 0. Why? Because you have a segment of length 1, you drop it on the plane, it's never going to hit your set because it's length 1. So it has 0 chance of hitting your set. And so we write up the final linear program. We want to maximize the density. We just saw that the density is sum of kappa t, subject to, and we have lots of constraints. First of all, the Fourier non-negativity constraints that the kappa variables are non-negative. We have the atomic non-negativity constraints. We saw this. We have that it's one avoiding. So this on the left-hand side is exactly your function value at 1. f1 equals 0. This is just what I mentioned a minute ago. Then you have that the atomic variables sum up to 1. This we had before. Then you have, these are crucial because you want to have connections between the kappa variables and the atomic variables. And this just testifies that whenever you pick a point z in a vertex in your witness graph, then you can take the probability calculated with atomic variables or kappa variables. They have to be the same, so they subtract to 0. And this also, well, I'm not going to go to details, but this also connects the kappa variables with the atomic variables. And finally, we have these old constraints, which we must not forget. These are the geometric constraints that the atomic variables sitting over a set K or a congruent set J, they have to add up to the same number. So the difference is 0. So you have all these LP, and this is the target that you want to maximize. And your task is to find a finite set X in such a way that this maximum is strictly smaller than 0.25. And once again, what you do is you launch a computer search and you try to find such a witness. So again, you are adding new and new vertices. You check your linear program, and you keep those vertices which seem to improve. You drop those vertices which are redundant, and so on and so forth. It's a highly non-trivial search, actually. So it's not just, okay, you try and you win. You have to really it's a very sophisticated algorithm. And at the end, we did find a graph on 27 vertices for which the numerical, for which the LP gave 0.247, so that is below 0.25. And at the end, of course, once you find this, then you are very happy, but then you have to really verify everything by symbolic calculation, not just numerically. So once you have a set, the edges really have to be length 1, not just it's about length 1. Numerically, it's okay. You have to make sure that it's okay. And to do that, you need to be in an algebraic field. You really need to make sure that the distances are 1. You need to make sure that whatever look like congruent triangles, they really are congruent triangle, and so on and so forth. So there is no cheating involved. And indeed, we did that. And then you need some error estimates. Why do you need error estimates? Because at the end, you need some LP duality argument. So what I wrote up is if we go back, so this is a primal LP, so to say, and it gives you a value. Then it's you would say, okay, 0.247 is my probably this is a good upper bound on the density. But to make it mathematically correct, you have to go to the dual LP and use a weak duality argument with the witness function, and there you can sometimes lose a little bit of the value, and indeed we lose in the 4th or 5th digit, but it doesn't really matter. Right, and this is the beam search that gave you the graph on 23 vertices. And maybe I should say that, I'm sorry to jump. Where did I say this? Well, at one of the slides, I hope I'm saying this, that this lives in a very simple algebraic field. So it's all the vertices of this graph live in the field of rationals extended with I times square root of 3 and I times square root of 11. And that's it. And this is just some numbers of how many variables we had to deal with and what's the running times and so on. So if you look at the last line, well, actually this is from a previous presentation. The last line, well, it should be 23. Well, it was 24, but one of the vertices was redundant. So at the end, it's just 23. But anyway, the number of variables, you can see that it goes up to 30,000 and the number of equations to 2,000 or so. And then the time to solve is something like 13 seconds. And the actual beam search has run for a good week on 128 CPUs. So it was a non-trivial computer search. And the result is that, oh, again, this should be G23. So 23 vertices. It's a witness to the fact that the upper density of any one avoiding set is less than or equal to 0.247, and this finally settles Erdős's conjecture. And yeah, I put here that the vertices of this graph are all elements of this field. So it's a rationals extended with these two very simple algebraic numbers. Oh, and maybe a last thing is the plot of the autocorrelation functions, because you see, given the Croft construction, you can plot the autocorrelation function, and then you can plot the autocorrelation function which comes out of the solution of your LP, and you can compare the two things whether they are close to each other or not. And the green line is the autocorrelation of the Croft. The blue line is the previous best linear programming result, which was unfortunately above 0.25. You can see 0.2544. So that's the blue line. And this is now the orange one is the current best, this work, 0.247. And you can see that the orange line indeed gets closer to the green one. Well, at the end, they will diverge a little bit. So, but this tells us two things, that probably the Croft construction is indeed optimal, because they really look very much like very close to each other. And the other thing is that, yes, the orange line does seem to be better approximation of the green than the previous of the blue. And so what's the ongoing work? Well, basically, there are two directions that we are going on now. One is a very interesting one, and it would be a major result, but I'm not very optimistic it will actually happen, is that to prove with this machinery that you need at least 5 measurable colors to color the plane. We know that 5 is necessary. Whether you use measurable or non-measurable colors doesn't matter, because Aubry-de-Grey's result just tells you that 5 is necessary anyway. But if you use measurable colors, then you can use this machinery, and you may be able to prove that you need 6 colors. That would be a pretty major breakthrough, and 6 is very close to 7. Still not 7, but it would be nice. And we have some preliminary results which are encouraging, but some signs are also discouraging. So I'm not sure if I can promise you that we can prove this, but at least we try, and there is some chance. And the other one is another famous problem. It's orthogonality avoiding sets on the sphere. So you take the sphere, and now you want to take a measurable set on the sphere in such a way that any two vectors are non-orthogonal to each other. And what's the highest density that you can achieve? And the conjecture is the so-called double cap conjecture, a fairly famous conjecture, is that the best you can do is to take a cap around the North Pole and a cap around the South Pole, which are just big enough to not to contain orthogonal vectors up there or down here, and they are separated far enough so that there are no two orthogonals from north to south, and that's the best you can do. You can calculate what the density of this is, and that's the conjecture that that's the best you can do. And maybe with these methods we can prove that, or at least numerically get very close to that. Right, and these are the references. One of them already published in Mathematical Problemming. This is the one that settles Erdős's conjecture and proves 0.247, and the other one is just on the archive, being submitted soon. Hopefully, we are just making last corrections to submit. So this is the one where we produce the graph with geometric fractional chromatic number exactly 4. And that's it. Thank you very much for your attention.
Thank you very much. Any questions?
In the proof of the chromatic number of the whole plane is at least 5, and a graph of 1581 vertex. How to construct the graph?
How? What was it? Yeah, it's 1,000
and more than 1,000. Yes.
And what was the
how to construct the graph?
How to construct?
The graph out of chromatic number 5.
Or how to prove? I don't understand that. Can you? Yeah, so that's the idea of Aubry-de-Grey, that he starts from some seed graphs, so from small graphs, and then he takes lots of rotated copies of it, and then maybe even translates them. So he does start from a small graph, which has only a few good colorings. Good colorings meaning 4 colorings. And then after the rotations and translations, he sort of excludes the possibility of a 4 coloring of the huge graph. And he proves that it needs 5 colors. It's not, I mean, and when I say he excludes the possibility, it's a computer search. So there are only a finite number of ways that you can start, and then you have to prove that you get stuck whichever way you start. And the clever part of the proof is, one, to make the construction, and then to see which which colorings you need to exclude, and then the computer search is well, it's kind of a small brute force program.
Other questions?
May I ask, what is the best solution that we had for this program? So what is the biggest number that we had?
For the fractional chromatic number and geometric, the geometric one, or the, well, so yeah, if I understand the question correctly, this is something I should have said. How far can it go up? So maybe tomorrow I find a graph with 4.1, 4.2, 4.7, 5.1. How far can it go up? And the answer is not very far, because whatever I find is gonna be less than 1 over the density of the Crofts construction. So when you take the Crofts construction, these small disks that I showed you that has 23%, you take 1 over 23%, that's about 4.36, and definitely the geometric fractional or fractional cannot go beyond 4.36, because if it did, if I found tomorrow a graph with geometric fractional number 4.9, you could tell me I'm lying, because that would prove that the density is less than 1 over 4.9, which is not true, because Crofts construction exists. So the truth is somewhere between 4, we just proved 4, and there is an upper bound of 4.36, and the truth must be somewhere in between. And there is a very natural thing to say that it's either 4 or 4.36. And I'm not sure. My feeling is that it's actually 4. But I'm not sure.
Other questions? Maybe one more question.
So do you think there are furthermore constraints that you can find to increase the estimation for delta significantly?
That's a good question. I'm not sure whether there are further constraints or whether this method itself, I mean, this method has not been completely exhausted. I mean, we do a computer search, we find something which proves 0.247, but if you do a better computer search, a more clever way to arrange things, you might prove 0.23 or whatever. So it may actually converge to the value of the Crofts contraction, even with this method. And whether to put further constraints, I'm not sure. I don't think you can. I think these constraints encapsulate everything already. So I don't think you can put further constraints.
We can take one more question if anybody else has a question. Okay, if not, let's thank our speaker again.